This is an honor to introduce Sunny this evening. She has completed a master's degree, I think, in forest ecology at UBC, and is now at UNBC in Prince George, doing some amazing work on sounds and acoustic monitoring, biodiversity, and the use of machine learning. I don't know anything about machine learning, so I'm looking forward to Sunny filling us in on what it means. Just briefly, about 4 years ago, 4.5, by an extraordinary coincidence, Sunny walked past my garden in Vancouver, and I said, well, nice to meet you, what, you know, and then somehow the subject got around to bird watching. And then I said, oh, I'm interested in doing sound recordings. And Sunny said, oh, I'm very interested in doing sound recordings. So the chance of this happening was so low. Anyway, since then, we've been good friends, and I've been learning a great deal from Sunny about processing data, how to use various kinds of apps, and all sorts of things I probably would never have learned otherwise. So thank you, Sunny. I'll hand over to you.
Oh, thank you, Peter, for the touching introduction. Yeah, it has been 4 years. I have to say, like, I'm learning from everyone a lot as well. Yeah. So with that, I want to say thank you everyone for coming this evening for this talk. And it is my great pleasure to be here to present some of my work with all of you. Just want to make sure, can everyone see my screen? The slide sharing?
It looks great, Sunny.
Okay, thank you. And I also want to mention that, so our audience today, because I also invited some of my friends from Taiwan, so we got international audience in this group today. So it will be very exciting and it will be fun. I also want to mention, like, if you feel comfortable, you are welcome to turn on your video so that I can feel less lonely when presenting. So I can still see people and I will observe your facial expression. If someone's yarning, and I will try to make it more exciting. With that, I hope we will enjoy this evening together with some birds and machine learning. So the topic of the talk today is all about these two things, machine learning and birds. At the first glance, it might sound very not compatible. Machine learning is the field that we train the computer to build models and then ask the computer to calculate or to do faster analysis compared to human. And birds are the things that we we think about more like ecology, conservation when we think about birds. So what's the connections between those two? So that's what I'm going to talk about today. So first thing I want to ask everyone to do is that imagine what would you have in your mind when thinking about birding? So this is probably the picture that you think you have in your mind. So a person being quiet in a field, using binoculars, looking for birds, and being quiet listening. Because we know, especially in the forest world, forest birds, most of the birds are heard rather than seen in the field. So we have to be really quiet and really observant to notice the birds around us. But as a birder, you might notice if you go on a birding trip nowadays, this might not be the image you see. Instead, you might see something like this. So instead of like being quiet, listening to birds, holding your binoculars, people are looking down on their cell phone and they scroll through their cell phones. And by the way, the person in the picture is Peter. So Peter is using the cell phone to do birding. And why is that? So instead of like listening, we are more relying on cell phone. Do people know what's the reason? I think you must have heard or used this thing called Merlin. So there's a very powerful app that got developed about 2 years ago. It's called Merlin Sound App. So it's developed by Cornell Lab of Ornithology. Basically, using this app, you can record the sound of the environment sound by your cell phone. And the Merlin app can automatically identify the bird species by the sound. So itself, it's a machine learning AI algorithm. So actually everyone now using your cell phone, you are using machine learning already. So here I'm going to introduce some of the features to explain why Merlin is so powerful and so influential that changed everyone's birding habit. First of all, it's free. So you can download it free, you can use it for free. Second, it's available for about 1,544 bird species. So just by sound, it can identify 1,000 species already. Just for everyone's information, we have about 10,000 bird species in the world, which means this app can already identify about 1/10 of the bird species. And this 1,000 species mostly focus on North America and Europe, because those are the recordings that Merlin was trained based on. The next feature that get Merlin really useful is it's powered by eBird. Of course, because it's developed by Cornell Lab of Ornithology. So it's powered by eBird and it's connected to your live list. So if you're in the field and you record some sound from Merlin, it can automatically link to your live list. So you can easily build up your live list just by listening or using your cell phone to record the sounds all around. Okay, so if Merlin is so powerful, you will probably think that it will be very beneficial for ornithology research, right? So it can help us identify the species quickly, efficiently. But actually, the answer is not really. Why? Because Merlin is not open source. So what does open source mean? Open source means the software for which the original source code is made freely available and may be distributed and modified. So Merlin didn't release the source code that they trained the model. So we don't know how they build up the machine learning. We don't know the algorithm they are using, and we don't know the parameters of this machine learning methods, which is an issue for scientific research. Because most of the time we need to modify these algorithms or this method to adapt them to our research data. So if Merlin can only release the phone app, it's really hard to use it in scientific research. We need to gain some ability of this flexibility. So how can we do with that? So there's another technology that we can think of. So I'm going to introduce another algorithm, machine learning algorithm called BirdNET. So BirdNET Analyzer is another machine learning algorithm for sound identification that developed by Cornell Lab of Ornithology and Tseng University of Technology from Germany. So it's an international collaboration between two big organizations. So the same, I'm going to list the features about BirdNET, and then we can compare a little bit about Merlin and BirdNET. First of all, BirdNET is also free. So it has a phone app you can download, and the same, just by recording the sound in the field, you can identify the species it will reproduce. It will output a list of species for you. So this is very similar. But the next one is really cool. So BirdNET is able to identify 6,500 species around the world. So again, we have 10,000 species around the world. So this is more than half of the world's species, which is really impressive and fascinating. And I will explain why BirdNET is more powerful than Merlin in a minute. And this version is updated in 2023 June, so about 4 months ago. So it's like very recently updated. Next feature, so it's powered by eBird. So of course, because it's collaborate with Cornell, so it's also linked to eBird. And so if BirdNet is so powerful, then why like the use of Merlin still like way more than BirdNet? Like now, if you go on the street, people would know Merlin, but probably not everyone would know BirdNet. It's because you will need internet to use the phone app for BirdNet. This is quite a restriction for countries like Canada and United States, where you can easily go on a hike and then within 10 minutes, you are out of service. So this is not really helpful if you need an app that need internet to do analysis. Okay, so from this comparison, we can see, okay, so BirdNet is more powerful, but it's harder to use because it needs internet. But is it helpful for scientific research? The answer is yes, because it's open source. So open source means BirdNet upload all their source code on a repository that is online. So everyone can download their code and then run the model in their computer. They can modify the model, they can provide suggestions. So this open source feature help researchers to do modification for their specific research needs. It also enhances the collective efforts for improvement. So that's why BirdNet can keep updating their versions so quickly, because scientists from worldwide can contribute to this model and provide suggestions and provide ideas. And you can be creative in model application, and then so on and so forth. So there are a lot of benefits of getting this source code open source. And here I'm going to demonstrate, or I'm going to show two very interesting applications based on BirdNet to make everyone have a better sense about how BirdNet can work. So the first thing I want to introduce is called BirdNet Pi. So BirdNet Pi, I can show you here. So basically, it's a little mini computer called Raspberry Pi. So if you install BirdNet Pi into this little computer and you connect it to a microphone, so you can put this microphone in your backyard. And then this microcomputer can analyze the sound directly from this microphone and then output a table of bird list. So you can, and this bird list can be uploaded on your phone or your computer. So basically, you can sit inside your living room and then sitting in the sofa, and you can scroll on your cell phone, and you can know what kind of birds are singing in your backyard. You don't even need to be in the backyard watching the birds all the time. And you can also provide this beautiful table showing like which time of the day, which bird is singing, and it will provide the counts for you as well. So it's a very cool application for BirdNet. So it's called BirdNet Pi. And then I have one of this in my backyard, so I can see what kind of birds is singing in my backyard every day. The next thing that you can apply BirdNet is called bird weather. So bird weather is the next step of BirdNet Pi. So with BirdNet Pi, you can get the data locally. So you can see what's the bird singing in your backyard. And if you are willing to, you can upload your observations from your BirdNet Pi to this website called Bird Weather. So Bird Weather is a collection of these BirdNet Pi stations mostly in North America. So you can see simultaneously which bird is singing in which location. So it's like a weather report, and this is a bird report. So that's why it's called Bird Weather. So if you go on their website, you can see this report about like, which bird is singing in which time of the day, this kind of information. And you can even, if you have a friend like who has a BirdNet Pi in their backyard, you can even like take a peek which birds are singing in their backyard. So it's very cool and very fun. So with these two examples, we can tell BirdNet is really powerful in supporting all these creative applications. So after listening to the difference between Merlin and BirdNet, we can see open source can be powerful. And that's also the reason why most of the current ornithology research uses BirdNet for acoustic data analysis instead of Merlin. So we have learned a lot about Merlin and BirdNet. So next, we want to learn about, okay, so how does BirdNet actually work? So how does BirdNet work? So basically, it's a machine learning algorithm. And with machine learning, you have to train the machine learning, right? So like, it's the same as everything. We have to teach the computer to do the job. So how we teach the computer, how we teach BirdNet is by asking BirdNet to listen to a lot of birds so that, and we teach it, okay, this is from berry thrush. This is from yellow-rumped warbler. This is from the species, so that BirdNet can link the sound to the species name. By doing this, you need a big data set. So the data set that BirdNet is using is based on two sound libraries. One's called Xenocanto. Another one is Macaulay Library. So Xenocanto is those are the two biggest sound library in the world. Xenocanto is based on Europe in Netherlands, and it has about 800,000 sound recordings in the world. Macaulay Library is owned by Cornell Lab of Ornithology. It has about 2 million recordings. And why it has so many recordings is because it is linked to eBird. So if you are out doing an eBird and you record a sound and you submit your list, the sound you recorded, it automatically go to Macaulay Library. So that's why it's like expanding so quick. So 2 million recording. Just for your information, I personally like Xenocanto a lot. I'm the user of Xenocanto. Just want to support something outside of North America. But yeah, everyone has their own preference. Okay, so based on these two biggest sound library, BirdNet extract 500 training recordings for each species. For example, now I need to train black-capped chickadee. The BirdNet will extract 500 training recordings for black-capped chickadee, and then ask the model to listen to these 500 recordings, and then remember the feature of these recordings. So by doing this, the model can already identify more than 6,000 of species around the world. Okay, so when you're using BirdNet, what you need is a sound file. So for example, a wave file, and you run it through BirdNet, and the thing you will get from BirdNet is a table. So in this table, you can see, so BirdNet will tell you the start time and the end time of a bird singing. It will provide you the name of the bird with a confidence value. So this confidence value range from 0 to 1. So the higher the confidence means the more possible that the detection is true. So we can see the first detection is with confidence 0.94. So which means BirdNet think, oh, it's very possible that this detection is true. On the other hand, for some like lower confidence detection, like 0.14, ovenbird. So BirdNet think, oh, it sounds a little bit like ovenbird, but I'm not really sure. So that's why the confidence is low. So BirdNet didn't tell you true or false. BirdNet tells you this confidence value. Okay, so this is the general introduction of BirdNet. So we already know, okay, so there's a very powerful software that we can use for acoustic analysis. How about hardware? So we have to collect our field data to do any acoustic research, right? So now I'm only focused on software. And next, I'm going to introduce the hardware that we usually use to collect the sound in the field. So the technique or the machine we often use is called autonomous recording unit. So we are not using cell phone. We are not using like sound recorder, like typical sound recorder. We are using this autonomous recording unit. So I have one example here. If you can see my image, my video. So this is my, this is one of the recording units we use. So you can tell it's very, very compact, very tiny. It's just as big as your credit card. So we use this recording units to monitor bird sound activity. So, and you can use this sound activity to refer biodiversity of the environment. It's self-contained audio recording device. So it has a microphone here, it has a battery, it has SD cards. So from the input to output, everything is inside these little units. And the reason why autonomous recording units is different from other recorders is because you can pre-program the time of recording. So you can design, okay, I only want to record 4 a.m., 4 o'clock in the morning to 7 o'clock in the morning, and not other times of the day. Then you can pre-program this time schedule into this little unit. And then you can leave it outside in the field for a couple months. And then you can just, after you leave it for like 2 months, you can pick a sunny day and then go back to get the data back. So you don't need to stand in the rain to do the bird survey and being miserable or being cold and sad. So it's a really, really helpful study method that we can use. So you can see like, everyone can smile happily to the picture when we are collecting the data. And the only restriction for this autonomous recording units is the battery power and memory card capacity. So before you leave this unit to the field, you have to calculate properly to make sure it can stay there for 2 months to support the data collection. And here I just want to provide you an idea about the cost of this unit. So the equipment I have on my hand is called Audio Moth. It's made by Lab Maker, and each of this is about 80 Canadian dollars per unit. So it's actually not too bad. There's another expensive one called Song Meter. It's provided by Wildlife Acoustic. Each of them is about 700 Canadian dollars. It's like bigger with the LED screen, and you can have a little pad, you can control it. Anyway, so it's more robust, but it's way more expensive. So those two are the two most common devices that people use to do autonomous recording unit. And here I just want to show you like how this device, this device can be really good at recording things. And then here I have a recording that is collected by Audio Moth on 2021 March 5th in the middle of the night. And then I want to show you how it sounds like. Okay. Okay, so this sound is collected in the middle of the night. If we don't have this unit out there, then we will never be able to hear this very special sound. Like, anyone want to guess what kind of sound we just got recorded? Do you have any idea? Can leave in the chat or can speak out loud.
Barred owl.
Nice, Peter. Yeah, so it's like 2 or 3 individuals of barred owls calling in the forest. Yeah, we will listen to more barred owl just in a minute. but yes, it's a barred owl. Okay, so we have learned BirdNet and we have learned the use of ARU. So hardware, collecting the sound, BirdNet software to analyze the sounds. So the combination of ARU and BirdNet will be a very powerful tool. So how can we use it in ornithology research? So here I'm going to introduce 3 kinds of research topics that's actually in my PhD thesis. So the first question I ask is, how well can BirdNet do on field collected data? So I want to prove that BirdNet is able to identify the species well enough that we can use it. Second question I ask is, okay, so now we can identify the bird species down to a species level. Can we identify to individual levels? So we know it's a barred owl. Can we know which barred owl it is? So this is the second question I ask. The third question I want to ask based on this technology is, I want to do a broad scale avian biodiversity hotspot mapping. So that community monitoring of the whole big spatial temporal scale. So basically it's a proof of concept for the for the question 1, applications for other 2 questions. And we are going to introduce it one by one. Okay, BirdNet evaluation. How well can BirdNet do on field collected data? So in order to do this evaluation, first thing we have to collect data. So this is our study area in John Prince Research Forest. It's 3 hours away from Prince George and 12 hours away from Vancouver. So if you drive to north 12 hours, you will arrive John Prince Research Forest. So it's a very beautiful place, very remote area with a lake. So all the field sites need a lake. And we have this little lodge that is our field station. And so usually I spend about 1 or 2 months in the summer to do my field work there. And this is some pictures during our field work. So we will walk through the beaver dam and then walk through the mature forest log area and just get this ARUs up in different sites. And I just want to show you one picture that I actually just think I was in the field station like a month ago, and I saw northern lights in one of our nights, which is incredible. Like, yeah, it was such a magical moment in that area. Anyway, lots of good memories and lots of data collected in this John Prince Research Forest. So how we set up the ARU is we designed 66 study sites, and we set up each of the sites has one of these ARU. So we have 66 audio moths stay in the field. Each of them is about 3 kilometers apart because we don't want the sound to get collected overlap with each other. So because the sound transmission won't pass 3 kilometers, so we can make sure like they are not correlated. So 66, 3 kilometers apart, and we collect data from 2020 to 2022. So total 3 years of data. And we collect about 1,500 hours of audios. And then if you transform it, it's about 15 terabytes of data. Okay, sounds a lot, right? It's almost impossible for human being to listen to this 15 hours audio and then transcribe all the bird species out of it. But luckily, we have BirdNet. So we just run all this 15 terabytes of data through BirdNet. So how BirdNet works is really well. So BirdNet only needs 1/10 of the time for computing. So for example, we have 1,500 hours. You only need 150 computer hours to do the analysis. So 150 computer hours is actually not too long. So it's about 6 days. And then if you go on a trip for 6 days and just make your computer work at home, after your trip back home, you will get all your data analyzed. So it's actually really, really efficient. So if you make the BirdNet run through your data, what you will get is this giant table output. So you can get the year of the detection, year, month, day. So this is the time. And then you can have your site. So this is your space, so time and space. And most importantly, you will get this common name. So the species you get detected and the confidence. So confidence, as we just learned before, so it's ranging from 0 to 1. The higher the confidence, the more possible the detection is true. Okay, so now the question comes. Actually, in bird analysis, we don't want this confidence. We want BirdNet to tell us it's true detection or not true, right? Is there or not there? So the question is, how can we know the threshold for true detection? For example, if I set threshold as 0.5, all the detections above 0.5 is true. All the detections with confidence value lower than 0.5, I say it's false. So I can turn this confidence to true and false. But how can I know which threshold should I set? This is the question I want to answer. So in order to know what's the best threshold to set, we need to validate the data, which means I have to listen to the same set of data to evaluate how well BirdNet do. So this is called calibration curve. So here I use olive-sided flycatcher as an example. So I plot the confidence value that get output by BirdNet versus the proportion of true detections that is validated by me. So a good detection should look like this. So the y-axis, the x-axis is BirdNet confidence. The y-axis is the proportion of true positive. So the lower the BirdNet confidence should be correlated with lower proportion of true positive. So you can think it's like the probability of being true. So lower confidence, lower probability. And as the confidence increase, you can see the probability or the proportion of true positive get increased as well. So the higher the confidence, the higher the proportion of true positive. So this is what this curve means. And we can use this curve to evaluate the performance of BirdNet. Okay, so this is just one species. And next slides, I'm going to show you 19 different species, the calibration curves for 19 different species. Okay, so those are the 19 common species that get detected by BirdNet, and I reproduce the calibration curve for all of them. So from these curves, you can tell what kind of species that BirdNet has lower performance with. So lower performance means the confidence value needs to be high for true detection. So those are the blue line and the purple line. So you can see when the confidence is low, like 0.25, 0.5, the probability of true detection is still really low. Not until the confidence value hit 0.75, the probability gets higher. So these two lines are actually poorly performed for BirdNet. So what are those two species? Berry thrush and brown creeper. So when I was listening to the audio, I noticed BirdNet often confused berry thrush sound with the white-throated sparrow. So berry thrush has this monotone vibration sound, and same for white-crowned sparrow has this long sound whistling. Okay, and we can also tell the birds that BirdNet is really good at detecting. So we call it high performance. So high performance means the true positive is high even with low confidence values. So even though BirdNet says, oh, I only have 0.25 confidence, but almost 100% of the detection is already true. So those are the birds that BirdNet is good at. So like yellow rump warbler, red-breasted nuthatch, Pacific wren are like BirdNet is good at detecting. And this is because those three species or this good performance species, they have more complex sound. So they have more features for BirdNet to be picking out and then doing the identification. Okay, and then after knowing this calibration curve, so we have to think back about our original question. So how can we set the threshold for BirdNet? I produced this bar chart just to help us to do the threshold setting. So how we can read this bar chart is that, okay, so now, for example, we want to detect yellow rump warbler. If we set the threshold as the minimum value, we can keep 100% of the data because we are not filtering out any data. But we might have about 5% of false positive. So 5% of these detections are not true. But if we raise our threshold to about 0.5, we can only keep 10% of our detections, but we have high confidence that about 99.9% of our detections will be true. So it's actually a balance between how many detections you want to keep and how many proportions of them are true positive. So those are the two things you have to think when you set your threshold. And so this is for yellow rump warbler, olive-side flycatcher, ground creeper, and berry thrush. So I have all this chart for the 19 species that commonly detected by BirdNet. So we can just read one more for this. For example, berry thrush. So berry thrush is the species that BirdNet is hard at detecting. So if you set the threshold really low, you can keep 100% of your detection, but only about 25 of them are true detections. So you probably doesn't really want to set the threshold that low. You probably need to raise your threshold to like 0.75 to make sure most of your detections are true. Okay, so this is what I have done to evaluate BirdNet, how well BirdNet can do on field collected data. Next, I want to apply this BirdNet technology to answer two different questions. So the first one is barred owl individuality. Can we tell apart individual owls by their sounds? So why we need to do individual identification, just in general, because individual identification can help us to understand the interactions in social hierarchy between individuals. It can also help us understand the resources used and physical development, mapping individual territory. All this requires identification of individuals. And how people usually do this is by putting physical tags on animals or use GPS tracking. So if you put a tag, you know, oh, that's individual A and B. And GPS tracking, you can know where they are located. Or because physical tags and GPS tracking, you have to capture animals to put on tags. So it's a little bit invasive. So non-invasive way to do this is to observe physical features. So for example, you can observe the scars on the dolphin or the facial scales of a sea turtle, and you can record them and identify individuals based on these physical features. So physical tags, GPS tracking, and physical features are well established, but they need most of them need captures of animals and visual observations of the details. This is very hard for avian species, for birds, especially nocturnal species, because it will be very hard to observe any physical details on them, especially during the night. So how about vocal individuality? Because we can hear owls in the night as well. If we can identify them by sound, that would be really useful. So that's the research question for this chapter. So in order to know whether we can identify individual by sound, we have to get data. So the same, so we set up the recorders and we use BirdNet to run through all the data, and we got, in total, in 1 year of data, we got 454 barred owl calls and collected out from 10 different recording stations. Most of the calls are collected in March when they are defending territory because they have to occupy territory, protect their territory. So they call a lot. We also collected a little bit towards the end of the breeding season. Yeah, but it's like way less than the beginning of the breeding season. So it's between March to May. That's the main period of time we got barred owls. So because now I want to train my computer to do individual identification by sounds. I have to make sure I can hear the difference. So if my human ears can hear the difference of the owls in different sites, I will have more confidence that I can train my computer to hear the difference. So here I want to invite everyone to listen to these two owls. So owl 1 is from 1401, is from a 1401 site. Owl 2 is from a different site. And I want to ask you to listen carefully to see whether you can tell these two sounds are from different individuals. So this is the first owl. Okay, this is the second one. Oh, is everyone thinking? Can you tell the difference?
Yes, yeah.
Nice. Do you want to share what did you hear? What's the difference you hear?
The second one, they had a little double stop on it, a bop bop
Uh-huh.
rather than a
Oh, good catch. So it's the duration or the notes, of the final notes is longer in the second owl, is it?
I thought I heard it double, ba ba ba.
Boom. Mm-hmm. Good catch. Yeah. Yeah. So I hope that some of you can tell this actually are two different owls. It's really cool. Okay, so after examining different owls from different stations, now I feel like, okay, I can actually tell the difference by my human ears. So I can definitely find a way to train the computer to distinguish all these different sounds. So what I did is I used a technique called spectrogram to extract sound features. So spectrogram is a way to visualize the sound. So it's showing the time versus the frequency of the sound. And so this is the spectrogram for barred owl. So you can hear boom, 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 boom. So like 8 notes. And then out of these 8 notes, we extract 12 temporal features and 18 frequency features. So temporal features are duration of the note, interval of the notes, and total length of the song. So duration of the notes, 1 to 8 intervals, and then duration of the song. In total, we have 12 of them. Because I was thinking like, oh, maybe like some owls, they have shorter durations of here, they have longer notes of there. So maybe these features can help us to identify individual owls. Okay, frequency features, 18 of them. So frequency features means frequency range of the first note, dominant frequency of each of the notes 1 to 8, maximum frequency, minimum frequency. Okay, so based on this 30 features out of 454 calls, I then run a statistic algorithm called discriminant function analysis. You don't need to know the stats analysis. Basically, it's trying to classify different groups based on the features we collected. So here I'm going to show you the visualization of the result of this analysis. So this is the visualization of the discriminant function analysis. So each of the dot is one sound, one call, one detection of the call. And each color is the calls that collected from that station. So ideally, we want these dots to be dots with the same color to be centered as close as they can. And we want dots in different color with different colors to be separated. So that means the model can separate the owls from different stations. So we can see some stations, the model did really well. So like the orange one is different from the yellow one, different from the green one, and the light yellow one. But there are also some overlap in between. So that means sometimes the model can be confused by some sounds that's close to each other. Interestingly, in this model, we use 6 features out of the 30 features we extracted. And the first 4 most powerful features are the duration of the song, the intervals between notes, and the duration of the 8th notes. So the duration of the 8th notes correspond well as what we heard in our little experiment, right? So we heard there are double notes in the 8th one, so make it a longer notes comparing to others. So all these 4 are temporal features, which means temporal features might be more powerful than frequency features in identify owl species. So in general, this model achieved 85% accuracy in identifying sounds from different stations. So we want to ask, then why the model have this 15% error? Where this error comes from? So originally I was thinking maybe it's possible that the same birds was flying around and get picked up by multiple ARUs. So we have, even though we have each ARU 3 kilometers away from each other, and the barred owl are usually quite territorial, so they don't really leave their territory far away. But maybe sometimes they would fly to different sites and then call and get picked up by ARUs in another site, so that the model can be confused by this situation. So I was thinking, okay, so if this is the case that causing the error of this model, then the site that close to each other, they should have higher vocal similarity. And the sites that's far away from each other, they should have lower vocal similarity. So that if I can find this pattern that prove my assumption might be true. Okay, so, but that's not all I found. So I didn't find any correlation between the distance between sites or vocal similarity. So this might not be the reason that why our model is having these errors. So there might be some other reason or just random noise in this model causing the error. Okay, so this is our vocal individuality for barred owls. The final one, we want to focus on a bigger scale question. How ARU and BirdNET can help us to monitor bird biodiversity by their sound. So we are going to do biodiversity hotspot mapping. So it's a general review about how many ARUs we set up in the field study site. We have about 66 ARUs set up during the breeding season of the bird. So we collect a lot of data. The first question we want to ask, how many bird species are there in the research forest? So BirdNET output spit out 131 species. And then I went into each of them and validate each of them. So at the end, we got 69 species that get detected in our research forest. And how I do the validation is by listening and comparing with eBird and BBS Atlas. And I also created this bird research station sound library that people can hear all this sound that collected by ARU. Okay, so we have 96 species get detected by ARU. Next question I'm curious about is, okay, so how many of this is overlapping with the human observation species? So we compare the ARU species get heard by ARU compared to the species that get seen or get heard by eBird. So ARU detected 96 species, eBird 93 species. So very similar, but they only have about 60% overlap. So in total, we have 120 species in our field station. So in this 60% overlap means there are some species that is easier to be detected by ARU, some for eBird. So they have both different strengths in detecting different group of species. And this is the chart about like what kind of order of birds that get detected by each of the methods. Okay, finally, it's the exciting part. So now we know that ARU can detect 96 species. Can we know the richness distribution across 66 different sites? So this is the final output of the richness map. So in each of the ARU, we can, using BirdNET, we can quickly produce the species list for each of the sites. And this is the comparison of the richness between different sites. So we have 66 hexagons. And you can know, oh, maybe the sites that are closer to water or the sites that is corresponding, overlapping with conifer mature forest would have higher or lower biodiversity value. So by producing this richness map, we can provide some forestry management suggestions about how to preserve high biodiversity spots for avian species. So this is one very broad scale application of BirdNET and ARU. So with that, I'm going to wrap up about today's talk. So what we have talked this evening, it has been about an hour. So what we have talked about, first thing we learned is Merlin is a powerful tool to learn birding by ears. No matter you are beginners or you are advanced birders, Merlin has been so helpful in learning. BirdNET advanced ornithology research, given it's open source, because we can have freedom to modify and use it. BirdNET Pi can be a good way to start if you are curious about BirdNET. So if you look up BirdNET Pi on internet, they will have a very detailed instruction about how to set it up. And I introduced 3 research topics that get covered by my thesis. So BirdNET evaluation and individual owl identification and a broad scale community analysis. And this is a very quick review about what my thesis is. So there are more details if you are curious about it, then we can talk about it. Finally, thank you everyone, and I hope you can